So yesterday we talked about similarity. We talked about what it means if two figures are similar. And we talked about the fact that when two figures are similar, they look the same, but they have a different size. So all of their angles are going to be the same. They're going to be the same shape, but they're going to be different sized differently. So they're going to be proportional to one another. So one thing that we were able to do is if we knew that two shapes were similar to one another, we were able to find out side lengths about a similar shape using the fact that they were proportional. So we went back to something that we did in the first unit, which was use proportional reasoning. And here's just a brief example of something that we did yesterday. So we were looking at this diagram that someone drew of their room that was a scaled down version of their room, meaning that it's similar to their room. And we knew that the longest actual side of their room was 12.75 feet. And so that would correspond to the longest side of the diagram, which is 8.5 inches. And so we could use proportional reasoning. We could set up these proportional reasoning equations, right? We could set up these proportional reasoning equations where we have like this fraction equal to a fraction where we know these proportions are equal to solve for missing side lengths. And so that's something that we did with similar figures yesterday. And another thing that we knew yesterday was that the angles in similar figures are also equal, the corresponding angles. And so we looked at these similar triangles, and we could tell by the way that these things were named that certain angles had to be equal, right? So if angle A equals 32 degrees, then the first letter in the similar triangle, angle X, also has to be 32 degrees because of the way that the triangles are named. Okay, so that's just a little brief summary of what we did yesterday. And basically, if we're told that two shapes are similar to one another, then we have all sorts of information about the two shapes, or we can figure out certain information about the two shapes. Okay, the goal of today's class is to be able to determine if two shapes are similar to one another. So given certain information, can we say, are these two shapes similar or not? Can we justify that? Okay, so let's just make a list. What do we need to know to say that two shapes are similar? Okay, so the first thing that we need to know is that all sides are proportional. Okay. So what that might look like in a picture is that thing that we talked about at the beginning of yesterday's class that relates to like a scale factor, right? One shape might be a scaled up or a scaled down version of the other one. So if I take a quadrilateral, I'm just going to make something up that looks, I don't know, maybe like 2, 5, I don't know, 4, and 7. Okay, and then I take another one, and I make this one, maybe I'll make it smaller, 1, 2.5, 2, and 3.5. Okay. Well, these sides are proportional to one another because what I've done from the first shape is I've multiplied all the side lengths by half. So there's a proportionality there. Okay? Or if you want to go the other way, if my original shape was the smaller one, right, and then I've scaled up the smaller one, I have doubled all of the side lengths. So there's like a multiplicity factor there. I've multiplied them by something. Okay, if I'm starting with the bigger one, I've multiplied them by a half. If I'm starting with the smaller one, if that's my original, then I've multiplied them by 2. Okay, so that's one condition. The second condition, and you have to have both, it can't be either or, is that all angles must be equal. Okay, so for example, well, actually, let's just add to this diagram, right? We'd have to know that this angle over here equals this angle over here, right? And the way that I'm going to depict that or notate that on the diagram is I'm going to use symbols to indicate that the corresponding angles are equal. So I'll use the same symbol for each corresponding angle. Okay, so I'll use this sort of arc in this bottom left corner, and then maybe I'll use a dot in the top left corner, and then I'll use a star in the top right corner, and you can use whatever you want as long as they're the same. And then I'll use like a heart maybe in the bottom right corner. Okay? You don't actually need to know what the values are, you just need to know that they're equal. Okay? Now, we are going to get into this tomorrow, but for certain shapes, depending on the shape, certain shapes have specific properties, and so for certain shapes, you may actually need to know less information. Hint, hint, triangles, okay? But in general, these are the two pieces of information that you need to know, and it has to be both. So maybe put an and here. Can't be either or. Okay, to know that two shapes are similar. And just to show you why not, here's a counter example. Okay, and I think I actually may have shown you this yesterday really briefly, but if you took something like this, where you have, let's say, a rectangle that's 1 by 2. So this is a rectangle, and it's 1 by 2. Let's say you double the side length, and now you make it 2 by 4, but instead of making it a rectangle, you make it into a parallelogram. Okay, well, yeah, there's proportionality with the side lengths, but the angles aren't equal, and you can see visually these are not similar to one another. Okay, so you must have both. Okay, and similarly, like I could take a rectangle that's 1 by 2 and change it into a rectangle that's 1 by 4. So I'm going to like elongate it, and then the angles are the same, but it's obviously not a similar rectangle. Okay, so you have to have both. All right, so we're going to go through some examples now and just say, are these similar or are they not? And I want to remind you here of something that I've been saying throughout this unit and throughout the last one, which is that you cannot rely on your eyesight to justify whether or not two things are similar. You can't say they look the same, therefore they are similar. You have to say that they meet those two conditions that we just listed above, meaning that all sides are proportional and all angles are equal. So we're going to look at these two shapes over here. Okay, well, they're both pentagons, that's good. They both have 5 sides. You can't have like one that has 4 sides and one 5 sides be similar. That wouldn't work. Okay, they look like they could be similar. Okay, let's see if we have enough information here. Now we know 2 side lengths. Okay, we know this guy here is 5 and this guy here is 2.5. And this guy here is 6 and this guy here is 3. So if we look at the ratio of side lengths, let's say we look at the big over the small. Okay, well, 5 over 2.5 equals 2, and 6 over 3 also equals 2. So that's a good start. But do we know all of them? We're missing 3 side lengths. Okay? If we're missing 3, we don't have enough information. We must know all of them. to say that these two shapes are similar. So because of the fact that we are missing 3 side lengths, we are missing certain information, okay? The other thing that we're missing is that we have 3 angles that were equal. And we can tell that because we can see that we've got an X here and an X here. We've got this sort of arc here and an arc here, so those 2 angles are equal. And we've got a dot here and a dot here. So those 3 angles are equal. But we do not know about the other 2 angles. We don't have information about that. We don't have a little box where angle U is or a box where angle D is. So even though they look like they're perpendicular, we can't assume that. Okay? And we don't know what this reflex angle here is where angle S is, or what the reflex here where angle B is. So even though these look like they could be, and they may in fact be similar, we don't have enough information. So we can't tell. Not enough information here. Okay, we are missing 2 side lengths. No, sorry, 3 side lengths on each pentagon. By the way, pentagon, I'm using that word, but pentagon is a 5-sided polygon, 5-sided shape, and we're missing 2 angles. Okay, so there's not enough information there to say that they are similar. They may be, but we cannot say for sure. Okay, let's look at the next one. Zora says that the 2 rectangles below are not similar because 60 over 50 does not equal 100 over 30. Is Zora right? Explain. Okay, so let's see what Zora did. Zora compared the top to the top and the side to the side. Okay. Now, when we are comparing rectangles, we don't want to compare top to top and side to side. We want to compare dimensions. A rectangle is not made up of a top and a side. That's not what defines a rectangle. A rectangle is defined by a length and a width. And so those are the things that we need to compare. Okay? So the length is the longer of the sides, and the width is the shorter of the sides. So if we look at the larger rectangle, the length is the one that runs vertically. So this is the length. I'm going to label it with a capital L. And the width is the one that runs horizontally, which is over here. Okay? And on this other one, the length is the one that runs horizontally, and the width is the one that runs vertically. So basically, I've just changed the orientation. Okay? We need to compare not top to top and side to side, but length to length and width to width. So we need to make sure that we do that. So let's see what happens when we do that. When we compare length to length, length over length, we get 100 over 50, which is 2. And when we compare width to width, we get 60 over 30, which is also 2. So because these 2 proportions are equal, these are similar. Okay? All right, let's look at the next one. Determine if the 2 parallelograms ABCD and Wxyz are similar. Okay, well, we have to bring in a little bit of what we know from parallel lines here. Okay, parallel lines. Parallelogram means these 2 lines are parallel, and these 2 lines are parallel. Okay, so we're told that this angle down here is 70 degrees. Okay, that means this guy over here has to be 110 degrees because these are interior angles on the same side of the transversal. Those are supplementary. Okay, and then similarly, This guy over here is 70 because these two are also...
Can I speak to a facility operator to room 255? Facilities to room 255.
Sorry for the interruption. Are also, same thing, interior angles on the same side of the transversal. And then if you follow it along, so is this one. So this is 110. And then we can do the same thing here. This is 70. This is 110. This is 70. This is 110. So we've got one of our conditions met, which is that all of the angles are equal. That's good. Okay, equal angles. Check. Okay, now if we compare, though, the shorter side to the shorter side and the longer side to the longer side, or like the slanted side to slanted side, base to base kind of thing, what we will find is, okay, let's maybe call this, I don't know. Well, actually, let's call it, we can call this side over here AB. And this side over here, WX. Okay? So if we compare AB over WX, we're going to get 8 over 6, which reduces to 4 over 3. And if we compare the bases, we can call this part BC and this part XY. We're going to get BC over XY. That is 12 over 8, which is 3 over 2. Okay? Now, these proportions are not equal. So the sides, the corresponding sides, are not proportional to one another. Okay? Therefore, these are not similar. Okay? And then finally, Janelle states that increasing or decreasing the sides of a given figure by the same factor will always produce a similar figure to the original. Is this true? Give one example that illustrates your answer. Okay, so the key word here is factor. Okay? Factor implies that you're multiplying by something. When you're multiplying by something, then you're going to have proportionality, right? If it said, she stated that you're increasing or decreasing by the same amount, like you're increasing or decreasing them all by 2, then that would be an adding thing or a subtracting thing. That would not create a similar figure, okay? However, when you're using a factor, then there is multiplying, so that is going to create something that's similar, okay? So for example, if you start with something like, I don't know, a triangle where this is 1, 2, and 3, and you multiply them all by 3, then you're going to get something that's 3, 6, and 9. Okay? All right, so that's it for this lesson. What I'd like you guys to do now is this homework over here, page 269 to 270. And I will hopefully see you guys tomorrow.